So today, we're going to crack open the Analytical Engineer's Toolkit. We're going to explore the incredibly powerful methods they use to understand, measure, and, perfect the very materials that build our modern world, from the medicine we rely on to the phone that's probably in your hand right now.
It's one of those questions you probably don't think about much, but the answer is absolutely crucial to our daily lives. Think about it. The fuel in our cars, the food we eat, our safety depends on engineers knowing exactly what something is made of. And that certainty, it doesn't come from guesswork. No way. It comes from the powerful techniques we're about to dive into.
Okay, so how do engineers make sure things are made right? Well, it really boils down to two fundamental approaches. You either prevent problems before they even start, or you find and fix them after the fact. This creates this core tension between what we call quality assurance and quality control. On one hand, you've got quality assurance, or QA. This is the proactive side. It's all about designing the process itself to prevent defects from ever happening in the first place. Think of it like creating the perfect recipe and setting up your kitchen before you even start cooking. Then, on the other hand, you have quality control, or QC. That's reactive. It's all about testing the final product, looking for any mistakes that need fixing. This is like taste testing the dish right before you serve it to make sure it's perfect.
But before you can even think about controlling the quality of something, you have to answer a really basic question. What is this stuff? And that brings us to the first pillar of chemical analysis.
This is qualitative analysis. Its entire job, its whole purpose, is identification. So if you've got a sample of some mysterious white powder, qualitative analysis is what tells you if it's sugar or salt or something else entirely. It's the what in our investigation.
But of course, knowing what's in a sample is only half the story. The next logical question, and honestly often the more critical one, is how much of it is actually in there?
And that's the job of quantitative analysis. It doesn't just tell you that there's caffeine in your coffee, it tells you there are precisely 95 milligrams of it. It's all about measuring the amount, the concentration, the dose. It answers the how much question.
So here's the really crucial point you have to remember. These two questions, what is it and how much is there, they form the absolute foundation, the bedrock of analytical chemistry. Every single sophisticated machine and technique we're about to look at is designed to answer one, or sometimes both, of those questions with just incredible precision. So, how do we actually answer these questions in the real world? Well, one of the most powerful tools in the box is spectroscopy. It's this fascinating field that lets scientists see a molecule's unique chemical fingerprint just by watching how it interacts with light. And often, it's light that's completely invisible to our eyes.
To kind of get our heads around this, let's look at a molecule we all know and breathe out, carbon dioxide. Now, based on its simple, symmetrical structure, you might think it would be kind of boring, maybe even invisible to certain types of analysis. Well, you'd be wrong.
And right here is where we see the magic of infrared, or IR spectroscopy. Even though a CO2 molecule looks perfectly balanced when it's just sitting there, its atoms are constantly vibrating. They're stretching and bending and wiggling around. These little molecular dances create a fleeting electrical imbalance, and that's just enough for the molecule to absorb very specific frequencies of infrared light. By measuring exactly what light gets soaked up, we can identify that molecule with total certainty. It's so cool.
And the real-world applications for this one technique, they're staggering. Seriously, IR spectroscopy is used everywhere, from figuring out the exact structure of new molecules in a lab, to making sure our medicine and food is pure, to detecting tiny amounts of pollutants in the air, and even in forensics, analyzing fibers and drugs found at a crime scene. Okay, but what happens if your sample isn't just one pure thing? What if it's a complex, messy mixture of stuff? Well, you can't really analyze it until you pull all the components apart. And that's where chromatography comes in. A great way to think about it is like putting a drop of ink on a wet paper towel and watching all the different colors spread out. It is truly the art of separation.
One of the real heavy hitters in this field is gas chromatography, or GC for short. And, just like the name says, this technique is an absolute master at analyzing any substance that you can safely turn into a gas.
So how does it work? It's basically a 5-step dance. First, you heat the sample until it vaporizes into a gas. Next, an inert gas, something that won't react, sweeps that vapor into a long, super thin column. Inside that column is a special liquid coating. Now here's the crucial part, separation. The different components in the gas mixture interact with that liquid coating differently, which makes them travel through the column at different speeds. Finally, as each separated component exits the column one by one, there's a detector waiting there to analyze it.
And what about mixtures you can't turn into a gas? Well, there's a counterpart for that. High-performance liquid chromatography, or HPLC. It works on a similar idea, but instead of gas, it uses a high-pressure liquid to force the sample through a column that's packed with tiny solid particles. This allows for incredibly precise separation, even for really complex liquid mixtures. All right, we've gone through a lot. QA versus QC, qualitative versus quantitative, spectroscopy, chromatography, but let's zoom out for a second and connect this all back to the real world. Why does mastering this analytical toolkit truly deeply matter?
At the end of the day, what's the goal of all this? It's all about innovation. It's about, as one source puts it, the ability to select, design, and create stronger, lighter, cheaper, and more efficient materials for innovative products. I mean, this is how we build a future, by developing better materials for literally everything, from aircraft and electric vehicles all the way to the medical devices that save our lives.
And you know, these techniques are constantly getting better, more sensitive, more powerful, faster. So the final question isn't just about what we can build, but what can we discover? As we get to peer deeper and deeper into the very nature of matter itself, what fundamental secrets will our material world reveal to us next?